Okay, we have seen the various types of the reactor, basically the fixed bed, packed bed reactor, in which there are the fixed bed, moving bed, and the fluidized bed reactors are there that we can use it for the catalytic reactions. Now, for selecting this particular one, selection of catalytic reactor is basically based on what? Its nature of the reaction. Important is that. And catalyst use. So this is our heterogeneous one, this particular reaction. So to obtain this particular design of this particular reactor, optimum design, so base design you can see in this particular one is generally the two reactors in such kind of the reactions in series, and that may be the different. Suppose for example, if you take the highly exothermic reaction, in case of the highly exothermic reaction, we may use the fluidized bed reactor and then fixed bed reactor. So this is generally we prefer in case of the highly exothermic reaction. So in case of the most of the catalytic reactions, single reactor may not be the sufficient because of the change in the rate conversion with respect to temperature as well as the, we can say, the activity of the catalyst. So there are basically two difficulties generally we encounter in designing the catalytic reactors. What are that two difficulties? One is that how we can account the non-isothermal. Basically, the problem is with the non-isothermal behavior. So, how to account non-isothermal? And another problem is non-ideal behavior. So these are the two issues generally we can see in case of the fluidized bed and packed bed reactor. So these are the two major concerns. One is that non-ideal flow and non-isothermal. Non-isothermal, that is in the packed bed reactor, and non-ideal one is in the fluidized bed reactor. Now take the case of that packed bed reactor with heat exchanger, either maybe the kind of a shell and tube kind of things, or you can say it is a kind of a standard packed bed. Suppose this is our packed bed. So we are giving the jacket for cooling. Okay. It is packed. Or what is the other case? Either you can have that some different kind of the reactor cooling arrangement. You are providing the so it's packed with the catalyst. So cooling will be from here. Is it? This is for cooling. Is it? And maybe the gas in, gas out. Is it? Now, in such cases, what may happen? Now it is exothermic reaction here. So definitely the temperature will increase, is it? But that you have to maintain by providing the cooling. So what will happen? At this surface or near to this one, wall will be cooled first and then so on. So there will be the temperature difference, significant temperature. That means here will be the high and here will be the low temperature, which is somewhat equivalent to coolant. So if you draw the kind of a figure, simply figure for that, say the packed bed. Suppose this is the and it is cooling for this one. And inside the temperature may be there around 150 or 200. And as we are providing the cooling, so this temperature may be reduced to around 100 degree wall temperature. So there may be the zone kind of this will be the 100 and so and so and so on. In the center line, there will be the around 150 to 200 degree. So center line will be always hotter than walls. Suppose if I put the TC and T wall, so definitely it will be the greater than this. And in this center line, your reactant will be more rapidly consumed. Hence, there will be the always radial gradient. That means, suppose here, so this gradient will be always there. That means dC by dr, or for temperature dC by dr. So this temperature gradient and concentration gradient will be always there in case of the this kind of the reactor. So to avoid such kind of things, so different situations are used. That's why it is shown that stage kind of the reactors, adiabatic reactors has been used for getting the better performance in our catalytic reactor. So you can see that one of the figure. So various kind of the stage adiabatic arrangements we may be using chain. That means suppose this is the one right here first. This is a stage. So in this case, stage, that means there will be the different reactors which are in the series. Generally we use it, and depend on the exothermic endothermic nature, there may be the intermediate removal or provision of the providing the heat. Say that Q and so on. So this kind of the arrangement generally we prefer it. So for exothermic reaction, if you plot the curve for conversion, and this you have studied, I asked to revise the chapter number 1. I don't know how many of you have done it, but if you see the chapter number 9, there you can understand the effect of temperature on the reaction for various reaction. So for exothermic reaction, and this is in the chapter number 9, okay? Remember. To say for the exothermic reaction. And if you plot conversion with respect to temperature, you will get the optimum curve like this. And optimum operating condition will go like this, and you have to use the stages to achieve this particular one. Is it? So this will be the optimum, because you have to maintain this one, otherwise you cannot get the conversion, proper conversion. And this is the optimum. You can revise this one, okay? This is from the chapter number 9. And if you are going for the exothermic irreversible, this is for reversible, exothermic reversible reaction. If it is a irreversible, you may have to operate at a constant temperature. So that that one is at T max, maximum operating temperature. I hope that you have solved the certain examples also. So it will be kind of a optimum temperature that you can use it. and this is for exothermic reaction. In case of the endothermic, it will be some reverse of this particular one. It will be kind of a, so you have to again operate this at the T max to get the maximum possible conversion. Is it? Say that temperature is, you can maintain constant temperature. So these are the three kind of the nature that you can get it for the various kind of the reactions, say that exothermic reaction, and this is endothermic reaction. Now for this, you can just see the simple example. Here is that example. So various configurations that can be used it, say that to design catalytic reactor, and that is basically based on your which curve, RA 1 upon RA and XA curve. For any of the reaction, you have to plot this XA and RA, but again this XA and RA is the function of again temperature. So to get the maximum value of RA as well as the conversion, we have to maintain it, and the different configuration like the stage, recycle reactor, mixed flow, plug flow reactor will be preferable, that we can decide it based on the optimum temperature progression. If you recall your CRE1, you can see such kind of the figure. There. This is for the optimum temperature progression, and you can see that there was an equation that you might have seen. XA is equal to Cp delta T upon minus delta Hm. Is it? So this particular optimum temperature progression curve figure is for XA versus T for various RA value. So if you fix the RA value, then you may have the different curves. Like this one, this one, this one. But finally the locus, if you take it, it will be like this. Is it? So this will be the, will go down, with this, and this will be the RA. This will be the RA will get increased. So if you go for the higher value of the RA like this. So here we need RA also and having the maximum. So we must have to operate at this particular to get it the higher conversion. So simple examples, if you see in your CRE1. I asked to go through the solved examples before coming to this particular chapter. I don't know how many of you have done it, but the typical methodology has been given that how to get the volume of the reactor for this particular kind of the system. But here the heterogeneous system, so we'll go for the weight of the catalyst, then the heat duty, and the suitable configuration for this one. So just we'll go for the one simple set of the parameters and go for the example. So that single reactor so here we are treating this particular using this reactor with 100 moles per second of reactant. First order reaction. Reversible reaction is first order. Feed conditions, that is 300 Kelvin. Feed pressure, that is at 2.49 megapascal. Maximum allowable is given as, that means beyond this there may be the shoot up of the reaction or maybe the degradation of the products may be possible. So we have to maintain the temperature below this one. We need the product TP, that is product, at 300 Kelvin. Other parameters, you see the from the figure, that is delta HR is given as minus 800, sorry, 80,000 joule for pure A. Then there is K1. K1 is given as exponential of 7 minus 83700 upon RT, meter cube per kg second. For this reaction, okay, that is minus RA gives that is in moles per kg of the catalyst hour. This K prime. K2 prime is exponential of 18. Having the same unit. And heat capacity is given as for both. If there is inert, same heat capacity. Okay. So this is the data that is given for the particular system, that is a single packed bed reactor, adiabatic packed bed reactor. Now, based on this particular one, we have to perform the design calculations. That means finally the heat requirement for cooling, heating, etc., and the weight of the catalyst with changing the field. Here it was mentioned for the pure one, Fa0, that is pure A. having the, so we have to find out for XA is equal to 0.8 and the feed having 1:7. That is A and inert. That means suppose it is 100 meter per second, sorry, mole, it is mole. Mole per second is pure A. So total will be what? 800 moles per A plus inert will be the feed. So for this particular one, we have to design the reactor. Now, the important thing is that whenever we are going to solve any example, so based on the whatever data is given, you should think what things you can calculate first. Is it? So from these data, what you can calculate? There is a relation for adiabatic one, that is XA and delta T. So definitely CP is given and delta HR is given. So slope of this particular line you can get it. I hope that all of you have noted this particular data. So now I am moving. Okay. Now, if you recall your chapter number 9, what is the relation for X and delta T? If you write it, if there is a change in the delta HR also with respect to temperature, we have X is equal to Cp prime delta T minus delta HR Cp but in our case this is the constant. So this will become, is it? Now total Cp will be what? There are 8, is it? 8, we can say that moles are there, feed having the, so it will become 320 joule per Kelvin. Delta HR is 80,000. So Cp will be what? The slope of this Cp upon minus delta HR. Is it? It will come, but yes, or it was mentioned 1 upon 2. So this will be the your slope, is it? It will be in the per unit Kelvin, is it? Now go to this particular figure, that is optimum temperature progression, which is given for this reversible reaction, is it? Now allowable temperature is given as maximum allowable 900. Okay. So we take it, we will not go up to it. We'll just take the little bit less of that one. We don't want to go up to the 800 degree because it is on the higher side. So we'll go for, sorry, 900. So select the lower than maximum permissible temperature. So max, so T we can select, it should be less than T max. So we can take T as a 800. You can take 850 also, no problem. 800. Now, for this particular reactor, we are taking the maximum as 800 degree, which we are reaching because of the exothermic nature. And conversion, possible conversion is maximum conversion we needed 0.8%. Okay. So here 0.8. So we are getting this point. Okay. See this figure. If it is asked in the exam, you should keep it ready, this figure with you. Before examination, I will just say that even you are not directly, you can do it on the book, or you can just take the Xerox of this particular figure. Before examination, I will just give the list of the figures that you have to keep it ready with you. That means Xerox of that particular figures, enlarged Xerox you can keep with you. Here the temperature we have taken 800 degree, that is allowable less than the maximum allowable temperature. So the and conversion we are getting 8.8. Okay, that is 80%. So we are getting this particular point. Is it? Now from this particular point with your slope of what? You see the slope? Slope is 1 upon 250. So you can draw the line. So you'll get the line which is intersect at 600 degree. That means what? So your operating line is this one. So in reactor, it will start at 600 and then reach to the 800 with 0.8 conversion. But before reaching to the 600, it should be heated because feed is available at 300 degree. That means before reactor, there will be the heat exchanger will be provided to heat the reactor. Okay. Again, for 800 is the maximum temperature that we are getting from the reactor. But we need the product at 300. That means after this reactor, we need cooling. So heating will be here. That is from 300 to 600. That means MCP delta T will be there. And from here also, MCP delta T will be required for cooling. So heating will be there for this particular portion, and then cooling will be. So if I draw this figure, XA T. So it will be kind of the, this is slope, this is 600, this is 800. So definitely in the reactor, the feed must be reached at what? 600 Kelvin, and it will reach up to the 800 Kelvin. But feed is available at 300 Kelvin. So before reaching to this one, we have to the heating. Heat should be given, you can say that. And after this one, heat should be removed because this is the 300 Kelvin. Okay. This we can easily get. But what about this one? We have to find out the weight of the catalyst or the kind of the reactor, whether it is a kind of a, mostly when we are talking about this one, generally we may prefer the recycle reactor. So this, what will be this is depend on the, what kind of the curve, that is 1 upon RA and XA. So you have to read the RA and XA. This is our operating line. So for various, here will be, this point will be for the RA will be different, or using the rate expression, that is RA is equal to KCA minus K, sorry, K1, K2, CR. You can get the RA value. And K is the function of temperature. So effectively, RA will be the function of temperature. So this RA XA value, you have to get it. And that this, if you recall your CRE1, it will be like this. Definitely it will come like this. So by using this particular figure, Suppose this is 800, so this point will be XA is 0.8 and RA will be what? It is at this particular curve. So RA is around 5, is it? So RA is coming to be, it is not the 5, it will be, it is increasing in this direction. So RA for this particular one is 10 to the power minus 2. So it will be the 0.05. So for at this particular point, RA is 0.05 and then you can go it. And at this particular point, RA is around, RA is coming to which line? So if I say like this, so it may be somewhere around in between this one. If I go for the XA is equal to 0, it will be 0.03. So this way you can get the values of various RA for this particular figure. Okay. So you have to read the RA and XA for this particular operating line. So the data that you can get it for this is XA and RA. That is 0.8, which is given in the book also. This is solved example. Methodology we are understanding because slightly there may be the change. Suppose if I say that take the allowable temperature 700. So this line will be start from this particular point and with the slope it will maybe the parallel line. So it may reach to the maybe 500. Okay. So all data will change. So 0.78, 0.7 and so on, 0.6, 0.5, 0.2, 6.1 and 0. And the corresponding RA values 0.05, 0.1, 0.2, 0.225, so 0.2, 0.1, 0.05 and lastly 0.03. So this value you will get it. So when you plot this particular one, you may get the curve like this. Is it? Just starting from 0, so it will be like this and reaching to the 0.8. Now in such case, what kind of the reactor you prefer? We prefer recycle reactor. If you recall your CRE1. So rest of the calculation, I know that, I hope you know this, how to go for the calculations of this particular one. So generally we prefer and we are balancing this area with this area, that is minimizing the area under the curve so that, sorry, maximizing the this outer area so that minimum area inside the curve and having the minimum volume or minimum catalyst will be required. And you know this equation, FA W is equal to FA0. So using this equation, you can get the area under the curve. For this one, it is very straightforward, and for this one, and you can get the value of the recycle also. So these calculations you can do it. Okay. Short example, just revise your CRE1, how to get this recycle ratio and other things. And finally, you may reach to the weight of the catalyst and recycle ratio, that is R is how much it is coming, the recycle ratio. Yeah. recycle ratio will be R is equal to 1. For recycle reactor, this equation will be what? Modified to what conditions it will be modified? If you recall your equations, you can see that for recycle reactor, these equations will be modified. It will be what? This will be for recycle reactor. This equation will be R plus 1, is it? Will be dxa upon minus Ra, and this will be the, here it will be R upon R plus 1 XAF, and here it will be the XA. Is it? You can just recall these equations, and this is given on the page number, your chapter number 6, I think page number 136, 137. Recycle reactor. Recall this one. And you may reach to the value of W, you can get it. And in this case, it is coming to be around 480 kg. So finally, the design one will be, this is your pack bed, packed with the 480 kg of the catalyst. This is the your reactor. This is 800 Kelvin, is it? This is 600 Kelvin. This is feed 300 Kelvin. Here will be the heating we are providing, and that is 9.6 megawatt. Here is no conversion, XA is equal to 0. Recycling the stream, which is coming to be the temperature reaching to the 700 because of recycling stream. And here will be the XA is 0.4. This particular point will be the, you see this particular, this will be the 0.4. R is equal to 1. XA is this. Here you have the XA is equal to 0.8. And again, you need the product at 300 Kelvin. So heat will be there, but you have to remove that heat, and that is minus 16 megawatt. So this will be the complete, we can say, the design of this adiabatic single stage adiabatic reactor for a particular case. So in examination, it will be somewhat lengthy to do it, this particular one, but some portions may be asked, and you have to be ready with this figure because it's online, so I cannot provide you these figures. In offline, generally I provide the page of these particular figures. So keep ready with this one whenever will be the examination for this. So this particular optimum temperature figure progression, because you have to use this particular. Okay. So now we'll continue this in the next lecture. I again suggest that revise your chapter number 6 for recycle reactor. Chapter number 9, what will be the optimum temperature progression? What is the our that operating line equation for adiabatic conditions? Okay. Sir, can you explain again why we shift to 1 of 1? Because that is, without that, how you can find out the weight of the catalyst? Why we shifted to 1 upon Ra versus XA curve? We have to shift. How you can get these values? This particular curve, W upon Fa, because it is not a straightforward nature of this particular one. If you are directly substituting the Ra expression, that will be more difficult, and you cannot solve that equation integrally. Just for a W calculation, or it has other sign. No, it is for the W calculation. Without that, you cannot do it, because we have to perform this using only graphical method or some numerical method. So here we are going for the graphical method. Numerical methods are available because in the softwares, various softwares are there. So what they are doing, they are not plotting the curve. Even they are plotting, they are using the numerical methods to calculate the area under the curve. Okay. Okay, we'll continue in the next lecture.
Hello, sir.
Yes.
Sir, can you please confirm what will be the syllabus for our midterms?